Can you hear me? Can you hear me?
Yes, doctor.
Okay, let's continue with doing our best, okay? Okay, so the analytic solution we're trying to find is the solution to this differential equation. And I was asking if you recognize how much f of x has to be, okay? And in this case, you have no force distributed between 0 and L. That means that this is equal to 0. So in this case, okay, f of x is equal to 0 because there's no distributed force between the ends. And of course, the boundary conditions at left, it's hinged. So u at 0 is equal to 0. And on the right-hand side, okay, you see that P at L is equal to the force F. And we know that P is equal to EA du dx at L. Okay, so as we said before, we have that the derivative at L is equal to F divided by EA. Okay, so you have this equation, second order, you can integrate. You have 1, 2 boundary conditions, and you can check. I'm not going to do that. You have to do it at home. You have checked that indeed the solution is exact. Okay, you have to do it. Any questions, people, about this? Now the question is, why is it exact? Well, the answer to that is that in this case, the solution, okay, to this problem is a linear function for u. And that's exactly the shape of the interpolation that we assumed. So every time you assume the same function for the interpolation as the exact solution, the result is going to be that the approximation using finite elements will be exactly the same as the analytic solution. Okay? So in this case, that was the situation. We had the same function, linear function, for the analytic solution than the interpolation that we assume. Okay? Now, remember the procedure. In this case, we take only one single bar. That was the partition. We establish the interpolation. We deduced, using these relations from solid mechanics, we deduce the stiffness matrix. Okay, you can recognize that if you have a different element, for example, different material, different area, different length, the term EA over L will be different, but everything else will be exactly the same. Then you have to establish the equilibrium for the system. In this case, was one single element. We're going to do something more complex right now. Impose supports. Those conditions has to be enough in order to take the singularity away. That means that at least you have to have, in this case, one geometric boundary conditions. And then you have to recognize that there are two different subsystems. Okay, so what you have to do is first, you solve it for the unknown displacements. After you solve that first subsystem, you have to recognize that you have all joint displacements as known. They're known. So what you have to go in the next step is to find the unknown external forces. usually that means that you have to find the reactions on the supports. And what you do is you multiply the displacement vector times the stiffness vector to find the unknown reactions that you still don't know. Remember, a reaction is an external force which is acting on the system in order to impose these support conditions. It's an external. So you have to see it like that, external on the system. So the reference, the sign convention for the external forces, you have to remember that, okay? Okay, now let's do a more complex problem.
Doctor, sorry, which sign convention we're using? From the rules or the normal?
Say that again, please.
Which sign convention are we using? The one from the rules, when we use sagging and hugging, or
no? Right now there is no problem. Right now, there's no problem because remember this is axial forces. In the next chapter, I will give you the sign convention, and that will be the sign convention that we use for beam bending. Okay. Now let's do a second example, which is more complex. Okay. Okay, let's take now a bar hinged from its upper end and with its weight included. Okay, so we have something like this. Damn it. Too ugly. Let me erase, try to. Okay, let me try to draw a decent bar. Believe it or not, EA is a constant, okay? Now, the weight is acting. So in this case, we have to consider the specific weight of the material. The length, you'll see that in a minute. This is big L. Okay? So the weight is pointing downwards. Questions about these people, about the problem? Okay, so let's start by doing something a little bit more complex that we have done. Okay? Now, instead of seeing like this, let me rotate it and let me see it like this. I hope there is no problem with this. So this is this, but now the weight is pointing to the right. Let's call it W. So W is going to be the load per unit length. So that's the weight per unit length and points to the right. Okay, now this is local X reference system. And of course, we try to determine the displacement. See, any section at the position X moves to the right. So this is what we're trying to find. Okay? Now, instead of doing one single analysis, why don't we do something better? Why don't we do two elements. And now I'm going to show you something interesting here. So let's use two elements for the discretization. So here we have one joint, two, and three joints. So this is the element 1, and this is the element 2. And now what I'm going to do is I'm going to consider, for this case, that the length of both is the same. And I'm going to call the length is equal to little l. Okay, it's different than this one, which is large L. So the length of each element is going to be little l. Okay, now let's go. So now we have two elements. So we have the equilibrium of element 1. So we are going to have EA over L, and this is for element 1. In general, this product could be different, okay? And that's going to be multiplied by 1 minus 1 minus 1, 1. And then here is D1x of the first element, D2x of the second, of the first element. I'm sorry, this is wrong, this is wrong, this is wrong. They both belong to the first element. And on the right, we're going to include the external forces applied on the first element. Now, we do something similar for the second element. We say this is EA. Oh, Jesus Christ. This is EA over L. Now, in general, as I must insist, this product could be different. This, in general, could be different than this one, in general. Okay? So it's going to be 1 minus 1 minus 1, 1. And this is going to be the first displacement of the second element. This is the second displacement of the second element. And on the right-hand side, we have something similar. We have the first force, oh, this is 1, of the second element. And this is the second joint of the second element. Now, in this case, okay, you can see that both elements are aligned. So the x direction of the first element points to the right. And similarly, for the second element, the x direction points to the right. So in this case, we can do this with no problem, okay? If we have different directions like this, then we have to do something extra. And we will explain that in the next session. But in this case, since this is the simplest case, we can do this directly. Damn it. Okay, now we have to recognize something. This joint here is the second joint for the first element, right? But also, this joint is the first joint of the second element. So we can take advantage of that in the following way. So the second joint of the first element corresponds to the first joint of the second element. So in order to avoid, or in order to ensure continuity, what we have to do is, we have to set that the displacement of that joint, Jesus Christ. So we say D2x, the displacement of the second joint of the first element has to be equal to D1x of 2. Now, what else? This is what we call continuity. What else? We see that this joint, which is common joint, okay, could have some external force, this joint. Let's try to see if we can draw it with different colors. This force. Now, this is the external force, but this external force has to be splitted. So part of that will help the element 1 to be in equilibrium, and the other part will help the element 2 to be in equilibrium. So this is the total external force that we're going to apply in that joint. And this here is this part here. The other part is this one here. But we have to be certain that if we add these two, we have to recuperate the external force that we applied in that joint. Let's try to summarize that. Also, in that joint, the external force F, let's call it F2, has to correspond to the sum of F, the second of the third element, plus F of the first joint, but of the second element. So we have to say is that F2 in the x direction has to be equal to the first one. So it's going to be equal to EA over L of the first element And we have to say that this is minus 1, 1. And this is equal to d1x of 1, d2x of 1, plus EA over L of the second. And then we say 1 minus 1, because this corresponds to the first row. And it's multiplied by d1x of the second, d2x of the second. Okay, so we're going to do now 3 equations for the equilibrium of the 3 joints. But now, before we do that, since we are trying to, maybe we can get confused with the notation, we're going to do something like this. Okay, this joint here, okay, you see that it is the first joint of the first element. And this one here is in trouble because this is the second for one and the first for the other. So in order to avoid these problems, we're going to do a common labeling of elements. So let's establish a common labeling. So this is our system. And this here, we're going to call it joint 1. I'm going to call this joint 2. And this is going to be joint 3. This is going to be the element 1. And this is going to be the element 2. Now, in order to establish now the equilibrium, let's use this labeling in order to establish the equilibrium. So for the joint 1, okay, so we call it F1x, and it's going to be equal to EA over L of the first element, and then we go 1 minus 1. And here, since this is the first element, and this is joint 1, we simply say this is D1x. The other one is going to be D2x. And with this, I will end. I'm going to write this equation, this one here. So this D1x corresponds to this joint. This 2x is this joint. But this D1x of the second element is also the second joint. And this one here is going to be this one. So let's try it and before we break. So for the joint 2, so F2x is going to be equal to EA over L of the first element, 1 minus 1, and then we go D1x, D2x. And for the other one, it's going to be EA over L. I'm sorry. This is minus 1 and 1, sorry. This is minus 1 and plus 1. Here it is 1 and minus 1. And then the first joint is going to be D2x, and the second joint is going to be D3x. And we see immediately that for this one here, we can write this in the following way. So it's going to be EA over L1. This is negative. And the second one is going to be plus EA over L1 multiplied by this. But this is also multiplied by this one is EA. So here we have to add EA over L2. And the third one is this one here is going to be minus EA over L2. This is a row, and it's multiplied by D1x, D2x, D3x. And in this way, we are going to concatenate. We're going to link elements 1 and 2. We will complete this on Thursday. I'm trying to find a version of the class notes in Spanish that we used several years ago. If I find it, I'll try to send it to you. Okay, people, don't forget today is the homework. And after that, I'm going to publish today the next assignment, which is related to bars. I'll try to solve these Zoom problems, okay? So next session, hopefully we will not have this kind of problems. Okay, is there any, finally, is there any question, final question, people? Any final question? No? Okay, bye-bye.
Doctor, we respect
Okay.
the homework. The fifth topic, we can, it's necessary, we can do in program two methods, bisection and Newton rafter, or
Yeah,
only
both.
one?
No, both. You follow the instructions.
Okay. Thank you, doctor.
This is so easy. It's very easy. I'm sure you did that in numerical analysis.
Doctor,
Yeah.
do you need input the data, or I show the result?
Put yourself in Genesis Loyola's shoes. She tries to determine if you have done your work, if your work is consistent, and if the answers are not correct, she will try to tell you where probably the error is. So you have to give her enough information so she will be able to complete her assignment.
Thank you.
Okay, so neither to the left nor to the right. Not too much, not too little. Enough so we can understand what you have done. Okay, people, anything else? No? Okay. Bye now.
Very good.
Thank you, doctor.
Thank you, doctor.
You're welcome.
Thank you.